Hello, everyone. My name is Jack Davis, and I'm with the Idea Lab at Oregon State University. Today, I will be presenting our work, Scalable and Usable Relational Learning with Automatic Language Bias. Imagine you have data on tens of thousands of chemical compounds. You, as an HIV researcher, obviously want to construct a drug to cure HIV. But in order to begin, you need to know which structures of compounds may aid in drug development due to their anti-HIV properties. The data you have to solve this inquiry likely exists in several relational tables. One solution for answering this query is to apply machine learning, but what type of machine learning works best with the data? Relational learning is the best answer for this structure of data. It's relatively straightforward and only requires positive, negative examples for a certain data set. The output is a data log definition, as you can see in the bottom right. A data log definition is just a set of rules with each rules containing a number of literals to define that rule. The key to relational learning that separates it from other learning algorithms is that it leverages the structure of relational data. Now, you may be asking, why not just convert the relational data into a flat file dataset that's effective for other machine learning models? This is because those models assume that there's no dependency in the data, which is not true with relational data. Thus, they're inherently led to inaccuracy. Relational learning, on the other hand, considers and uses the dependencies in the data. There's also no feature engineering required, which is common for other models, and it's also very costly. Finally, the output is extremely interpretable for most domain experts. For the rest of the presentation, we'll use a simple example to describe relational learning. Our example moving forward would be a toy data set about papers and their authors. There are 6 tables that each have information about a specific paper or a specific author that's written a paper. We want to learn a relationship between the authors on whether or not they've collaborated in the past based on information we can find in the database. With the examples we have, we can see that Madden and Bayliss have in fact collaborated with each other, whereas Madden and Socher have not. Together, we'll walk through an example of how relational learning works using a bottom-up approach. This essentially means we'll use a positive example to create the most specific definition, which is just simply the definition with the most literals. Then we'll use other examples to generalize and shrink the definition until it can no longer improve. From the diagram on the left, we see that the first process is to create the most specific definition using the first positive example. The first positive example we introduce is Madden and Bayliss. We now add all the related tuples from Madden and Bayliss from the author relation into the data log definition. After we add them as constants, we must replace those constants with variables in the definition. Notably here, we change Madden and Bayliss to V1 and V2 respectively. We then iteratively add the tuples based on indirect joins with the information learned in existing atoms. These indirect joins join together a relation with the training example provided. See here, Madden and Bayliss also join over with author affiliation. For example, from the first atoms we added, we found an author ID, which can be used to join the author affiliation tables. We can now add more atoms. Notice there are 4 atoms added, but only 2 tuples in the relation. That is because the algorithm may add more than one literal per each tuple, where some of the attributes in the literal have variables and others have constants. Following the addition of the author affiliation literals, we can use another relationship between author and paper author, which we can then use again to add more literals to the definition. After exhausting all possible direct and indirect join paths between the tuples in the database and the positive example, we can conclude that we have the most specific definition. We introduce new examples into the algorithm to see if we can generalize the definition to cover more positive examples. We do this by testing the new example against the original definition. Originally, V1 and V2 represented Madden and Bayliss. We now have the same variables represent a new positive example, Socher and Manning. Since we need to generalize the definition to cover more examples, the definition needs to hold true for the new example. This means we must drop the MIT affiliation here, since both Socher and Manning attended Stanford and are affiliated with Stanford and not MIT. Once we drop the literal, the definition now covers the new example. Although the generalized definition covers more positive examples as it is less specific, it may also cover negative examples. So after each generalization step, we need to check whether the accuracy of the definition improves. We'll generalize the definition until it does not improve. We assess the definition by calculating the number of positive examples covered subtracted by the number of negative examples covered. In order to have an accurate definition, we want to maximize positive coverage and minimize negative coverage. As you can see here, by dropping the MIT affiliation literal, we have improved our coverage from 1 example to 2 examples. Since we have improved our definition, we continue on in the generalization process. We introduce yet another positive example, Madden and Stonebreaker. In order for the definition to hold true, we must drop the author affiliation with the Stanford affiliation. After this, we will continue to introduce new positive examples until the process does not improve the score from the scoring function. At the end of the learning process, we found that two people have collaborated with one another if they're co-authors on a paper. This can be read from the data log query as both the authors have their name on on the same paper, as you can see here by the variable v7, which represents the same paper name. The primary challenge inhibiting widespread adoption of relational learning is that it does not scale well with data. This is because the most specific definition over a large data set may become far too large with the extensive amount of joins possible. Additionally, scanning all related tuples may cause extreme overcomputation. Beyond the first step, the generalization process may take an even more significant amount of time. Between the size of the most specific definition and the computation needed for the scoring algorithm, the generalization step becomes far more computationally significant than in the toy example used before. The current approach to shrinking the necessary computation for relational learning is to assign manual language bias. This language bias essentially defines a set of joins or possible paths between literals that are acceptable. This restriction in join paths accessible is to the algorithm reduces the search space where the algorithm has to look for related tuples. This greatly reduces computation. As you can see using the example, you can join a path between author and author affiliation using the ID attribute. This relationship is an example of language bias. In addition to defining join paths, language bias can also assign whether or not a certain attribute in a literal can exist as a constant. As you can see here, MIT is a constant in the author affiliation. You can also decide which of the attributes are of a newly added literal have to be existing variables, so whether or not they exist in a prior atom, or whether they can be fresh variables. Not only do these restrictions allow for the most specific definition to be created faster, it also ensures for a shorter and more computationally friendly definition. While extremely beneficial, language bias is seen as sort of a black magic in relational learning. The process requires significant expertise for a given dataset. Even with the knowledge of the dataset, trial and error to develop the right bias is necessary. Personally, I've spent over 3 hours developing a set of language biases for a dataset that I had compiled and cleaned myself. Due to the exponential nature of join paths for a sufficiently large dataset, language bias can be extremely long and complicated. This is one of the manually tuned language biases for our empirical studies. And as you can see, there's over 100 lines of code for it. The basic intuition behind our system, autobias, is to use inclusion dependencies to find which join patterns are most beneficial to our goal of maximum positive coverage. One such relationship is the primary foreign key relationship. Autobias can operate with two types of inclusion dependencies. The first is exact inclusion dependencies, which are also known as referential integrity constraints. The main example of an exact inclusion dependency is a key relationship between relations. An example of this relationship is shown. The fact that paper author's author ID attribute is a subset of author's ID attribute is a form of a referential integrity constraint. This form can often be found in the schema or discovered from the database content. The other form of inclusion dependency is approximate. We calculate this by checking what percentage of values in a certain relation's attribute exist in another relation's attributes. If the percentage is set sufficiently high, then we can assume an inclusion dependency. For autobias, we use a standard 60% threshold. This is part of a pre-processing step taken by autobias to ensure that all relevant inclusion dependencies are known. We observe that effective definitions maximize coverage. We aim to connect attributes by using the most generalizable join paths, i.e., the join paths that share the most values. These patterns are typically the ones present within the inclusion dependencies. We then use the inclusion dependencies to find the connecting attributes of the most generalizable join patterns. The first step in the autobias algorithm to develop the language bias is to create an inclusion graph where each node is an attribute within a relation. Edges connect attributes together when they satisfy an inclusion dependency. For example, paper author has an author ID, which is a foreign key of author's relation, the author relations ID. This creates an inclusion dependency and thus an edge. The second step in the process is to assign a type for each node that is only pointed to and not away from. As you can see, the author relations ID type is assigned as author, and the professor relations ID type is assigned as professor. Both only have incoming arrows and not outgoing arrows. The next step is to propagate the types of each attribute backwards until the type reaches a node with no other outgoing edge. These rules allow for a node to take on several different types. For example, author's ID type is passed to paper author's author ID attribute. Additionally, professor's ID type is also passed to paper author's attribute author ID. As you can see here, paper author author ID now has multiple types, both author and professor. We also observe that attributes with a large domain are likely to not contain generalizable paths. This will lead to very little positive coverage. For the examples shown, we see that there are only 2 schools shown in the right attribute, author affiliation, but 5 values in the ID attribute. This shows a high cardinality on ID, but a low cardinality on affiliation. We have autobias determine whether or not attributes can be constant or not based on their cardinality. If the domain is smaller, it is more likely to be a constant within the context of the definition. So we assess the cardinality and based on the user defined threshold. And if it is lower than that threshold, we can assign constants in the data log definition. Additionally, autobias can automatically determine other aspects of the language bias, which we explained further in the paper. While autobias automatically generates language bias to restrict the walking space of the relational learning algorithm, because the definitions can still be very large, since there's a large likelihood of a lot of inclusion dependencies in the data, there are instances when the language bias is not restrictive enough and the algorithm is still computationally expensive. Thus, we aim to create a small and representative sample for the most specific definition in order to shrink the computation of the generalization step. Towards this goal, we contribute 2 sampling methods. Our first approach is to use a random sample of the most specific definition. However, in order to first generate a random sample, you would have to sample from the most specific definition itself. We want to consider the relatedness of the literals from the definition in our sample. But this way of computing random sample is inefficient because it first creates definition. We want to find a way to achieve the same goal without having to use the computation to build out the full most specific definition. We observe that creating a definition is an iterative application of semi-joins, starting from the first training example. We aim to return a sample of each semi-join without having to return and compute the full result. We are able to randomly select tuples with probability proportional to the level of connectedness within the data. Its connectedness is based on both direct and indirect connections. The benefit of this algorithm is that it creates a true random sample of the most specific definition without fully computing it, so it's very efficient. As I mentioned, this algorithm returns a true random sample of the definition. This is proved further in the paper. Notice here as we have achieved random sampling prior to the full most specific definition generation. We also implement an existing sampling method known as naive. This method simply chooses tuples throughout all relations, each with proportional probability based on the size of the relation that they exist in. This does not produce a true random sample, and it creates a bias towards small relations. Additionally, it ignores the connectedness of all tuples. However, naive sampling is much faster than random sampling, since there's very low computational overhead because you don't need to compute statistics on the dataset. Naive also performs well over databases with a small number of tables, or if there aren't very many tuples in each table. In these cases, it actually produces a result much more similar to a true random sample. While random sampling improves upon the bias of the naive method, it still overcommits to highly connected relations. The stratified method aims to give equal representation to all possible join paths by taking a random sample from each type of pattern. This is because the true most specific definition contains a diverse set of patterns. However, the stratified technique takes more computation than its naive and random counterparts because it needs to categorize all of the pattern types in order to sample from them. There also exists a computational challenge in the generalization process, specifically the scoring function. In order to score a definition, it's first required that the data log be converted to SQL and then ran to check both positive and negative example coverage. Due to the nature of data log, it's very possible that a definition could result in hundreds of SQL joins, which would cause a large amount of computation and thus a high runtime. We make this more efficient by checking if a definition subsumes the most specific definition. We do this by first building a most specific definition for every positive and negative example. Then in each step of generalization, To know whether the current definition covers an example, we check whether the definition subsumes the example's most specific definition. This is far more efficient as it reuses computations that have already happened. Moving into our empirical results, we test our language bias over the Castor relational learning system, and we also compare it to other forms of language bias. The first baseline we establish is essentially contributing no language bias at all. This means that all join paths are possible and all attributes can be constants. The second baseline is very similar, except we eliminate all constants from consideration. Finally, we compare our results to that of syntactic bias written by an expert. For our empirical results, we consider 5 datasets of varying types and sizes. Each database has an important target concept with ranging levels of positive and negative examples. For example, the HIV dataset about chemical compounds aims to learn which compounds have anti-HIV properties. Similarly, the SIS database about server activity seeks to learn a definition for which server processes may be malicious. In terms of pre-processing, which is the time taken to generate the language bias itself, the baselines both take no time at all. Whereas manual tuning done by a domain expert could take anywhere from an hour to a few days. This is because they may have to write up to a few hundred lines of code, and it could take significant trial and error to get that code to work. As you can see here, IMDb takes almost 112 lines of code just to get the language bias right. On the other hand, auto bias, which is only done once for each dataset, can extract language bias extremely efficiently when provided inclusion dependencies, and is also efficient when developing approximate inclusion dependencies. The times shown right here are pre-processing times to generate the language bias prior to being assessed by Castor. We use naive sampling to compare the auto bias solution to that of other baselines. We also assess the solutions by using an F1 score, which is a weighted average of precision and recall. The results of the first 3 datasets show that while auto bias has a slightly higher overhead for time, it learns with extremely similar accuracy to manual training. The overhead is more than made up in the time saved by not having to manually tune the bias. The first baseline also struggles to learn anything, while the second baseline, without constraints, runs with some accuracy, but on average takes much longer. We see a similar pattern in the second 2 datasets as we did in the first 3. Moreover, the 2 baselines, both of them show an inability to learn anything at all for the second 2 datasets. For the empirical results, it's clear that auto bias is able to generate language bias that is able to pinpoint the true accurate model. Moving into the sampling experiment results, we can see that stratified and random compare well to their naive baseline. You can also see that stratified does possess a small amount of overhead compared to the other 2 methods. From the results, you can see that both random and stratified don't perform as well to naive compared to the UW and SIS datasets. These datasets, however, are built for naive sampling, as UW has a very small number of relations, and very small relations with very small tuples, and the SIS database only has a single relation. Both of these are very conducive to naive performing well. We conclude that while relational learning requires a complicated language bias to be effective, there exist relationships in the data that allow this bias to be generated automatically. We show that auto bias is able to achieve very similar results to manual tuning across many datasets of varied structures. We can continue to, in the future, optimize pre-processing and begin to work on automating the relational learning process by identifying hyperparameters. Thank you.